And we are live.
Welcome to your Daily Dopamine with Dr. Joe McCullough, where we deliver daily doses of education.
Hey, more people. Hey, Disney, Dylan, welcome.
And get ready to be dopamine.
Oh, yeah. Hey, Swells One, welcome. Okay, thank you. You are very welcome. We are about to join Paul live. Ask a Physicist anything. And today, I'm going to let George Costanza again introduce the topic for the day.
George. Boss.
Hey, Lily. All right, let me just stop this so it doesn't keep playing. I'll just close that.
You want to hear the whole Seinfeld episode?
Okay, welcome. This is episode 12, I believe, episode 12 or 13.
Somewhere.
With Paul Graham, who's going to talk about absolute zero and temperatures below absolute zero. WTF? What the? You know what? Well, Paul, get away.
All right, welcome. So we talked last week, for those of you who are here, about what it takes to take a physical system, a gas of independent atoms, and cool it down about as close as humans can get to absolute zero. So these days, the relevant region for future work is nanokelvin. We're down to 100 or so nanokelvin, and still pushing toward absolute zero from there.
And Paul, just what is a nano?
Nano is 1 billionth, 10 to the minus 9.
So we're down to a billionth of a Kelvin.
Yes. So 7 people, if you look around and there's 7 people in the room with you, 7 people are 1 nano-earth worth of population.
Oh, that's good.
So a nanokelvin is a damn small unit of temperature. Now, the thing that sparked this whole conversation, though, is somebody mentioned that they had heard about an experiment recently that was able to give a gas a temperature that was actually negative. Not negative like below 0 Celsius, but negative like below 0 Kelvin. On the absolute scale where 0 actually means 0, there is still such a thing as a negative temperature. Now, you notice, we didn't say here temperatures colder than absolute zero, because as I'm going to tell you in a moment, actually colder is the wrong word for it. These negative temperature systems are actually, you could say, hotter than infinite temperature would be one way of putting that. But they are not cold. They don't want to suck in energy. They want to give away energy. In fact, they want to give away energy more strongly than even an infinite temperature system would. Now, what do I mean when I say that something in nature wants to do anything? Well, of course, that means I'm personifying nature and acting like it has an agenda of its own. But so sue me. I'm human, and humans are so centric on the way our own minds work that we want to personify everything as human. So nature wants to, these systems want to give away energy. What do I mean by want to give away? Well, one of the most powerful rules in nature is what we call the second law of thermodynamics. And this is one that, for anybody who's been watching the whole series, we've kind of brought up the idea of entropy more than once in the past, I think. But this is the idea that no matter what happens in the universe, it always tends to make the total entropy, the total disorder of the universe, go up. And when I say disorder, I'm not just kind of using the word vaguely in a way where, man, this room is full of entropy. Although if it's my office, it is. But the disorder is precisely defined mathematically. There's a formula for entropy. Because this is not really a mathematical series of talks, I'm loath to write the formula. So just consider it like an art exhibition. I'm just writing the formula to show that it exists. Entropy is the Boltzmann constant, which I wish wasn't there, times the natural log of omega. And omega is the number of different ways the system can be rearranged on a microscopic level. Point is, entropy is a perfectly well-defined concept mathematically. And what do I mean when I say an object wants to give away energy? Well, anything that nature wants to do is something that would increase the overall entropy of the universe. So if nature wants to move energy from a hot object to a cold object, if I put an ice cube in my cup of coffee and I notice energy starts flowing from the coffee into the ice cube, well, it's because that's what makes entropy go up. In fact, this is the way we define hot and cold objects. You may have learned in a science class once along the way that temperature is a measure of the average kinetic energy of the atoms in a substance. Well, no, it's not. I mean, that's a consequence of the way we define temperature, but the real definition of what temperature means in the first place has to do with what would it take to make the entropy go up. So, forgive me if I go over to a graph we put on the board.
Hey, wait, before we pause, I have a quick question. What did the Higgs boson say? Oh,
ooh, what did it say?
Lily, type that one more time. Oh, what did the Higgs boson say when it entered the church? How can you have mass without me? But don't bunch. Thanks, Lily.
Thank you, Lily. All right, so so what do we mean when we say something's hot or cold? Well, if I've got a typical gas, just like the nitrogen gas in this room that we're all breathing, well, some of you are breathing gas in other rooms since you're watching this on the internet, but I have confidence that everybody watching this is breathing some kind of nitrogen-oxygen mixture. If you were to take the atoms in this gas and you were to ask, what would happen if I gave them more energy? If I pumped in energy, sped up those atoms, gave them more kinetic energy so they're bouncing around more strongly? Well, one answer we would always give is that would be a description of a hot gas. If I take away their energy, I'm describing a cold gas. If I take away enough, the gas would liquefy. But if I were to ask myself, how much entropy does that gas have? How disordered are those molecules? Or if I'm thinking of that formula with the log omega in it, omega saying how many ways are there that I could rearrange all the gas molecules in this room and still have pretty much the same room full of gas? Well, the more energy I give them, the more disordered they become, because each molecule has more options on what it could be doing. It could be zooming around faster in different directions, trading the energy among other atoms. So in general, for most substances, as you increase their energy, their disorder, their entropy goes up also. However, since if I'm asking if something's going to happen spontaneously in nature, I'm always wanting to say, can I increase the total entropy of the universe? It turns out it is vitally important how steep this curve is. And you notice, at cold temperatures, the gas might not have as much entropy, but man, the curve is steep. The entropy is going up a lot with each new bit of energy I put in. As I go to higher temperatures, yeah, I've got more entropy, but the curve's starting to level off. It's not going up as fast as I add more energy. And in fact, that is what makes something hot, is that this entropy curve is getting shallower. Why do I say that? Well, suppose I've got two substances. One is really cold. It's down here on the steep part of the curve. And one is much hotter. It's up here on the shallow part of the curve. Well, if I could talk that hot system into giving some of its energy to the cold system, yeah, the hot one would lose a bit of entropy. If the energy goes down, the entropy went down a little bit. But the cold one will gain a lot of entropy. If the energy goes up by that same amount, kind of one comfortable finger's breadth on the board, kind of, then if the energy goes up by the same amount, the entropy will go up a lot. So what does nature want to do? Nature wants to give energy away from the hot object, give it to the cold object, and that is precisely what happens spontaneously when I dump that ice cube in that coffee. As a result, the total energy of the universe just went, the total energy of the universe did not go up. If that happened, Nobel Prizes for everybody who's at all associated with the discovery. No, the total entropy of the universe, went up when the energy flowed into that cold ice cube. So, if I wanted to, again, indulge me for a moment on the mathematics, the steepness of the curve, for those who have taken calculus, this is a derivative, which just means how steep the curve is, but this is saying how much does the entropy, which we call S, go up for each little bit of energy that we put in. And we call the answer beta. So that cold system, you could also call a high beta system. That hot system, you could call a low beta system. And you say, well, wait a minute, high beta, I thought we called it low temperature. And low beta, I thought we called that high temperature. Well, in fact, we do, the relation between beta and temperature is this. Beta goes as 1 over the temperature. Beta equals 1 over. Boltzmann's constant, that annoying constant in there again. But the interesting thing is the temperature on the Kelvin scale there. So, high temperature systems, I'm dividing by a huge number, so I get a real low beta. That makes sense. High temperature systems over here, we said it'd be a low beta. The entropy's not increasing as much. Low temperature systems, real high beta. And frankly, if you were to ask, what do I mean by hot and what do I mean by cold? Well, I could say hot means high temperature, but an even better definition is hot means low beta. It means a system that's willing to give away energy because it won't lose very much entropy. A low beta system is hungry for energy. It wants to take in energy because it'll gain a lot of entropy. Doesn't want to give away energy because it'll lose a lot of entropy. And again, nature is always looking for a way to increase the total entropy of the universe. All right. How does that lead to these negative temperature systems that you've heard about? Well, I said normally for an ordinary system, typical gas, as you ramp up the energy, the entropy keeps going up. It might go up more and more shallowly, but it keeps going up, all the way up to infinite energy. However, there are systems that are exceptions to that. There are systems where there's kind of a maximum amount of energy that you could reasonably give them. What kind? Well, what I've drawn here is supposed to look kind of like a bar magnet. I've got these blue lines here that are the magnetic field. So you could say, all right, I've taken any system. In fact, in the experiments we describe in a moment, we're actually not going to take a magnet made out of iron. We're going to take a gas that's been cooled to an incredibly low temperature. But you say, all right, I apply a magnetic field, and it turns out you can just kind of take this as a given, take this as one of the rules of the game we're setting up here, if it's not something you're already familiar with. Turns out in a magnetic field, a spinning charged particle, like a spinning electron, wants to line its spin up with the magnetic field. Actually wants to line its spin up opposite the magnetic field because the electron's negative. Damn you, Ben Franklin, electrons did not have to be negative. But it wants to line its own magnetic field up with that existing magnetic field. So if this is a little spinning electron, this is the low energy state lined up with the magnetic field. A higher energy state would be for this thing to be lined up against the magnetic field. And like I said, that nature wants, if I personify nature, to increase the entropy of the universe. Another thing you could say is nature usually wants to lower the energy of any system. If in doubt, you'd say, okay, this thing has more gravitational potential energy when I lift it off the ground, but I let it go, it returns to that low energy state. So these things normally, if I take a compass needle and I try to twist it around against a magnetic field, when I let it go, it'll spin back around and line up with the magnetic field. However, if I've got a microscopic gas and I've got all these spinning electrons here, and what I've written here is most of them are lined up with the magnetic field, and a few rebels are lined up against the magnetic field. So this is a fairly low energy configuration. Most of the electrons are in that low energy state. And this is a fairly low entropy configuration, not very disordered. In other words, I can kind of count on the fingers of one hand. I can literally count on the fingers of one hand how many of those atoms are spinning in the wrong direction, how many of those unpaired electrons in the atoms are pointing against the magnetic field, and it's not very many. So this is pretty organized. Most of them are all pointing in the same direction. So this is a low energy system, and it is also fairly low entropy. And now I say, suppose I ramp up the energy. Suppose I give it more energy by flipping some of these electrons against the magnetic field. Well, this would be a higher energy system. And it's also higher entropy. It's a lot more random looking. There's a lot more disorganization in the way those spins are lined up. Now you say so far, well damn it, Paul, that's exactly, entropy. That's exactly what you said always happens. So why is this such a weird system? I mean, if I were to think about this so far, I would say, I would say this doesn't look very different from that graph over there. I started out at low energy.
So real quick, people asking questions. We're going to let Paul go on with this, and then I will look back at some of the questions after we're done and see if we can use that for next episode. So I may not answer questions you guys are typing in.
Oh, although we might be able to get to them soon, because I'm hoping to hit a punchline here soon. So I start with low energy. All the electrons lined up like they should be, and low entropy. As we randomized the electron spins, we were going to higher energy because they're pointing against the magnetic field, some of them. We're also going to higher entropy because there's a lot more randomness and disorder here. However, if I keep on raising the energy, if I tried to make something where almost all of the atoms were lined up against the magnetic field, and maybe only an occasional rebel that was going with the magnetic field. So if I tried something like this, well, this is really high energy. Almost all these atoms are lined up the wrong direction, and wrong meaning the high energy direction, just like this is the wrong place for this pen to be compared to the desktop. So they're almost all lined up in the high energy direction. So this is high energy. But they're also very organized. Because they are all agreeing with each other, that means this is low entropy. Now, by the way, if I were to ramp the energy up even more, and I were able to, say, shatter whatever forces are holding these atoms in place in the crystal lattice, then I might go to very high entropy, because then they'd be like all over the room and they wouldn't be organized in that lattice anymore. But if I can keep the lattice intact, but I start getting more and more of them pointing the wrong way, the entropy does not keep going up, it drops. That is something that you did not see on our ordinary gas over there. What does that mean? Well, remember, I said beta is the steepness of this curve. A steeper curve means a system that wants to gain a lot of energy because its entropy will go way up. A shallow curve is a system that kind of wants to gain energy if you got some available, but it doesn't really care. Its entropy wouldn't go up very much, so it's willing to give away energy if it can give it to somebody who needs that energy more. Generous of it. At this point, we hit zero curve. So this is high beta. This is low beta. Now we hit something that we never got on that other curve, which is zero beta. Now let's pause right there for a moment. What does beta mean in terms of temperature? Remember, we said beta essentially is the inverse of the temperature, the reciprocal of the temperature. So high beta means cold, low temperature. Low beta is high temperature, so it's hot. Zero beta is actually infinite temperature. This is how this system would behave as I ramp the temperature to infinity. Now, I haven't really ramped the temperature to infinity because I haven't melted the crystal, but you could say that at least in the approximation where I leave the crystal, the atoms in their lattice positions, at maximum entropy, it's acting like it has infinite temperature. But what the hell happens over here? What do I make of negative beta? Here I've got slightly negative beta. Here I've got extremely negative beta. What does that mean? Well, if I said that low beta means the system's kind of willing to give away energy because it won't lose very much entropy, negative beta means the system actively wants to give away energy, even more than something at infinite temperature. Something at infinite temperature is actually totally indifferent. They'll say, yeah, you want some energy? Here, take some. And anything else at less than infinite temperature will suck up that energy from it because its entropy will go up. But now we got something that says, even if I'm just giving the thing away, if you gave this thing a chance to give energy away to something that had zero beta, infinite temperature, it would, because it would say, I don't care if that other guy's not gaining any entropy. I'm gaining entropy by giving away energy. So this is not, now this is negative beta. And how is beta related to temperature? Well, it's 1 over temperature. So if I were to kind of think how beta and temperature relate to each other, I put temperature on this axis and beta on this axis, well, it's kind of a curve like this. Low beta means high temperature. High beta means low temperature. Well, shit, negative beta means negative temperature. In fact, even if beta is just barely negative, like I'm just past the top of this curve, that's actually a temperature of almost negative infinity. Now, does this mean that this system, once I've kind of got more than half the atoms against the magnetic field, does that mean that this is a very cold system? Well, no, just the opposite. It's very hot. It wants to give energy away. It wants to give energy away even more than something at infinite temperature does. So the flaw is that we've been thinking of temperature as the fundamental way of measuring this thing we're talking about. That was just the wrong choice. We should have started over way back in the beginning when we were first measuring the hotness and coldness of things. We should have defined it in terms of beta. All along, we should have been saying cold means high beta. Hot means low beta. Negative beta means hotter than hot. So it's that, it's that 1 over that shoots this curve to plus or minus infinity that makes this kind of a little bit more confusing than it might have normally been. So you can get negative beta. You can get extreme negative beta. Yeah, that means you've got a negative temperature. And again, this isn't negative like below 0 Celsius or below the freezing point. This is negative on an absolute scale. This is a temperature below absolute 0. But you don't say colder than absolute 0. In a way, what you've got is a temperature hotter than infinity, which is still pretty damned impressive. So,
Paul, real quick, do you want to just review the whole system? So this doesn't apply to ideal gases. This is a very specific kind of system.
Yes, again, the reason why I was able to do this is because this system where the only thing I'm allowed to change is flipping the spin of these electrons. Either they line up with the magnetic field or they line up against the magnetic field. But I'm not allowed to melt the crystal or move the atoms around or have them zooming around in different directions. That is the reason why once I started approaching the maximum energy with all of them lined up against the field, the entropy didn't keep going up, it went down. But this is a very unusual kind of system where that can happen. Now, can we make that happen in real life? Up until a few years ago, the answer was no. I mean, you could say, if I could arrange a system of spins in that weird way where most of them were lined up against a magnetic field, then yeah, that would be negative temperature or negative beta, but I've got no way of actually making that happen. However, this being 2016 instead of 2006, now I can answer yes. They have made this. Researchers in Germany at the Max Planck Institute, Schneider and Bloch are the names of two of the main people in the group. What they managed to do, and I had heard they had done this. I didn't know how they had done it. And what I was imagining was, oh man, they must start with one of these, spin systems, and they must meticulously find some way of taking each of those spinning electrons and flipping it around against the magnetic field, and do that with more than half of them. I felt like an idiot when I read what they had really done. They don't meticulously flip these around against the magnetic field. They prepare a gas at almost absolute 0. It is a gas of, I think they were using potassium atoms or something like that. But each one is held in place. The reason why they're in this nice organized checkerboard pattern is they've got a lattice of laser beams. And we talked to you last time about how you can use laser beams to manipulate very cold atoms and move them around. They have got each atom trapped at one position in this lattice by this crisscross pattern of laser beams. So the atoms cannot move away from these positions. That's important because they can't do what a normal gas does, where the atoms just start moving more and more quickly in random directions and the entropy goes up as you increase the energy.
Do you have an idea how many atoms are we talking about? Order of magnitude?
I don't know the answer to that. So Joe just gave a question, how many atoms are present in this gas? I think it's a small number. I mean, I think if I said a few hundred,
yeah,
that it would be more like that than what you normally think of as a gas, which is, you know, a few times 10 to the 23rd or something like that. And the reason is, again, each atom is locked in an individual position where these laser beams cross, and that's not an easy thing to do with 10 to the 23rd atoms. So yeah, each one is in an individual position. Most of them are lined up with the magnetic field because it's cold gas, so they're almost all in that lowest energy state. And then they don't take the atoms and flip their spins. They just flip the damn magnetic field. This is why I felt like an idiot when I realized that. They flip it this way. And now all of a sudden, those few that used to be against the magnetic field are now lined up with the magnetic field. All the rest of them, the vast majority of the atoms in that gas that used to be pointing with the B field are now pointing against it. Now, ordinarily what would happen is that means the gas would just scatter, and all of that energy that was just released would go into kinetic energy of those moving particles. However, they got these things locked in place with that lattice of laser tweezers. Thanks, Steve Chu. That's an awesome technique you developed way back when.
It's also preventing them from flipping.
Well, they can't flip without exchanging energy with one another. So any one of them can flip, but that energy's got to go somewhere. So if one of them flips, another one will flip back the other way. So yeah, essentially there's nowhere for them to put the energy if they were to try to flip. So you have now gone from this part of that energy versus entropy curve, which was very high beta, meaning very cold, to this part, which is very low beta. So now you're not just low beta, negative beta. So if you've got negative beta, yes, you've got negative temperature. But what you have just made is not the coldest substance ever recorded. Interestingly, the same lab that might be working at nanokelvin temperatures, which is the coldest temperatures ever recorded, can then flip it around and, I mean, yeah, strictly speaking, they're getting negative temperatures, but what that really means is they are getting negative beta. That is the hottest substance ever recorded, not the coldest. So that sample of gas in the laboratory, in a thermodynamic sense, is hotter than the core of the sun. Now, if you say, does that mean it's going to spew out huge amounts of energy and burn down the laboratory? No, it doesn't, because again, the whole point here is we've restricted, the way that we could get the gas into this weird state is we've restricted the options that are available to it. The gas molecules can't gain kinetic energy. If they could, we say, well, what if that laser beam fails and the gas molecules can go wherever they want? Well, then all of a sudden the entropy curve is going to change back to something a lot more ordinary, and you won't have a negative beta system anymore. So it's not like they've got some huge amount of untapped energy reserves in there and we're barely holding it in check. No, the experiment's perfectly safe. I mean, you wouldn't want to freeze your hand on it or something like that. But the only reason why we have this crazy U-shaped entropy curve is because we've given the gas very few options on what to do with any energy that we give it. So it's kind of, as you give it more energy, it runs out of options on what to do with that energy, and its entropy starts going down instead of going up.
So quick question, Paul. So most of us think of temperature in terms of hotness and coldness.
Yeah.
If I put my hand in something that's really, really, really hot, it's going to burn. If I put it in something really cold, it's going to freeze. So in terms of thinking temperature that way, if I could put my hand into this system, what am I going to feel?
Hot.
Hot.
Now, again, what you're really going to do is disrupt the lattice and the system's going to stop behaving this way. But if you could put your hand into a system that could somehow still remain this way, it would want to give energy away to your hand even more strongly than something at infinite temperature would. Now, again, that doesn't mean it's going to incinerate your hand, because presumably after giving you even a little bit of energy, it'll have climbed back over to the other side of this curve. But if you could somehow prepare a vast system that was negative beta, and it could stay that way even as it gave energy to your hand, then yes, that would be dangerously hot. As it is, it would be kind of, you know how you can reach into the oven and pinch a piece of tin foil, and the tin foil doesn't burn you, but the walls of the oven would? It's not because the tin foil is less hot, it's because if you pull even a little bit of energy out of it, it cools. This would be kind of the same way. Yeah, it's infinitely hot, But if you pull even a little bit of energy out of it, then it's not that hot anymore. But yes, this is, when you talk about hot and cold, this still, here you've got cold. High beta means cold. It means the thing wants to suck energy out of its surroundings to increase its entropy. Low beta means hot. It's willing to give energy away from its surroundings. Zero beta means infinitely hot. It's willing to give away energy even if the surroundings had no plans for what to do with that energy, no way to increase their own entropy. This thing says, what the hell, I don't care. I'm not getting any use whatsoever out of this energy. It's not increasing my entropy at all. And negative beta means hotter than hot. It means this thing now actively wants to give away energy, because by doing that, its entropy will go up. So rather than, if this thing were ice cold and I touch it and it freezes my hand to it on a cold day or something like that, instead of saying, oh man, that's cold, what I should say is, son of a bitch, that's hot, that's high beta. You got to get used to it, but yes, high beta is cold. Low beta is hot. If I drink a coffee and it's at 99 degrees Celsius, oh man, that was some low beta coffee. Let's see, whether you call spicy food low beta or not, man, that's chemically low beta. Man, this could get very geeky very fast. However, as you go into negative beta, strictly speaking, if you're still going to say temperature is 1 over beta, then you got to call that negative temperature. But what you have really done is gone from high beta, that was cold, lower and lower beta until you hit 0 beta, and then you just smoothly continue on into negative numbers. You say, okay, slightly positive, 0, slightly negative. It wasn't a dramatic transition there. And again, on this graph, it's kind of like if I move smoothly along the beta axis, my temperature numbers go nuts as I pass the origin, but maybe temperature isn't really what I should have been thinking of in the first place. Maybe this beta is actually a better concept for measuring what we call temperature.
Awesome. Any questions from our live members?
Did they use the potassium because it's a group 1 metal with a single unpaired electron?
I know they used something with a single unpaired electron. I'm only moderately even sure that it was potassium. But this is why they would not use a noble gas, for example, is no unpaired electrons, so nothing to line up with or against the B field. So they use something with a single unpaired electron, Any questions from random scattered internet people?
Any quick questions dealing with this or future topics of conversation? Now's your time. While we're waiting, Paul's going to dance around like a monkey. No.
How do monkeys dance?
If not, then if you do have questions, go to one of my YouTube videos. How many have seen Big Bang Theory? People really, I've got to watch the Big Bang Theory. I can't tell you how many times I've heard that.
I know who the characters are because you always see them quoted and stuff, but I've never seen an episode.
Here's a question. How do we apply this to superconductors?
Ooh.
We have never talked about superconductors, have we?
Okay, let's make superconductors a thing soon. This particular thing, as far as I know, you can't apply to superconductors. However, the conditions under which metals go superconducting is extremely low temperatures. So this whole branch of physics, low temperature physics in general, definitely applies to superconductors. I am not aware of any way in which this, particular trick for making a negative beta system would suddenly lead to a breakthrough in superconductors. But in physics, everything is connected to everything else. If you understand one thing better, you usually end up saying, oh, holy crap, now this makes sense, and this makes sense, and this makes sense. So there's when people ask what is the practical applications of the such and such piece of research, I always feel like they're missing the point. You don't know what the applications are because you haven't yet figured out what they're going to learn and what other things are suddenly going to fall into place and make sense. So, but as far as I know, there is no direct King's Highway from negative beta systems to superconductors. But give them a little time, and we'll see. We'll see which Nobel Prize address of 10 years from now says. And the thing that finally made it click for me was, thinking about those negative beta systems.
We have more requests for blowing stuff up with liquid nitrogen.
Blowing stuff up.
Lily, next time we get liquid nitrogen close to a Wednesday, we'll play around with it a little bit.
Yeah, but let's get that damn liquid nitrogen tank we've been talking about, yeah.
Could you pose a cycle of beta, negative beta to alter the energy flow, possibly?
To alter the energy flow?
Like,
possibly. I'm not sure what energy flow we're talking about.
yeah, I'm not quite sure there, Dylan. But it's about time for us to wrap it up. Thanks so much, Paul Graham. Woo! Stay tuned next week. You have to be the two best teachers ever. Aw, thank you. Well, definitely, Paul. Have a great, guys. Thank you so much for tuning in. Hope to see you next week. Possibly superconductors, possibly something else.
We will come back to superconductors before long, yes.
Yes. All right. Have a great day, everybody. Take care.